Okay, what happens when we take a simple harmonic oscillator and we add friction? We add what's called a damping force. Well, what's going to happen is the amount of energy is not going to remain constant. Now, previously, we saw that with the simple harmonic oscillator, we're trading potential energy for kinetic energy, and it's just going back and forth, but the total mechanical energy of the system remains constant. It's also true for the pendulum. But now we are going to add a non-conservative force. We're going to do work on it by this non-conservative force, and this is going to take energy away from it. All right. Now, we need to go back to our equation for the simple harmonic oscillator, okay? Starting with Newton's second law, force equals mass times acceleration, okay? That means that the total force acting on a system is going to be equal to the product of the mass and the acceleration. So what are those two forces? Well, we still have our restoring force from the spring. That's Hooke's law, negative kx. But now we're going to introduce a new force, and this is going to depend on velocity. Again, this is an okay approximation. The drag on a simple harmonic oscillator, depending on how the fluid flows around it, can go by v or v squared. But here we're trying to keep everything as simple as possible. And we add this little term right here. So looking at this, again, we see that the restoring force is going to be always opposite to the direction that's stretched out, and x is our displacement. Now, this other force depends on velocity instead, okay? So whatever direction it's going in, drag is going to slow this down, all right? So here's our drag. Here is our Hooke's law force. Okay. Now, we want to convert this into an equation with different derivatives, a differential equation. That's what we had the last time. And before, we converted our acceleration into the second derivative with respect to position. Those of you who've taken calculus recognize this. Our velocity becomes the rate at which the position changes as a function of time. And since we're moving the two equations, the two terms on the right to the left side, they go from negative to positive. So this is what our equation looks like. Okay. It's a linear equation. Okay, it's not nonlinear like we had the problem with the pendulum. It is a second order differential equation. But previously, our position as a function of time looks something like this. We had amplitude times cosine omega t. Depending on how you do different things, you could do sine omega t or cosine omega t plus some phase, but that was basically it. What this additional term does, okay, this drag term, here's our drag term right there, it adds this decaying exponential, okay? Adds that decaying exponential. And if you remember, a decaying exponential, e to the negative, some constant x. When we graph that, it looks something like this. Actually starts at a point. Okay? So this exponential decay is a very common thing that we see in physics, we see it in math. And what it's basically going to do, it's going to say, all right, our cosine is still going to oscillate up and down, whereas our negative exponential is going to decay. Okay, so we'll also have two constants here. They're not as important. We have this first constant, which is really the decay constant. It connects this part of the exponential to this, and we're going to still have our angular angular frequency. I always want to say angular speed, angular frequency. Okay. Now, you don't need to, memorize these different equations, obviously, but you should, understand what that produces when we graph it. Again, if we're just to graph the cosine part would, oops, wrong tool. The cosine part would just oscillate up and down, at a constant amplitude. With the decaying exponential, if we just did the e to the minus alpha x, we would just see this part of it. So we combine the two, oscillation plus exponential decay, we get something that looks like this. And this is what we call underdamped harmonic motion. Looks terrible. But this is what would actually happen if I put a mass on a spring and I just allowed it to oscillate up and down. There would be friction involved, okay? But because it's slowing down more and more, the rate at which the amplitude would decrease would be an exponential decay. All right? All right. That's typically the case. If we go back to this equation here, that's typically the case. That exponential decay with the oscillation, where this term is smaller than this term. Okay? Basically, oops, B is less than K. That's the way I should write it. All right. Not exactly, but, imagine that. What happens if I make that viscosity term, that damping term, really, really large? Well, once I make B large, okay, the movement is going to be so restricted, it's not even going to be able to go through one oscillation, okay? Remember, the Hooke's law part of it wants it to oscillate up and down. But if I make the friction so large, not only is it going to rob it of a lot of energy, it's actually going to slow it down so much that it never even is able to make one complete oscillation. And we get that profile that we see in C. We call this overdamped because the friction is so large, harmonic motion. Okay? Now, if I balance my frictional term with my restoring term, okay, I can get the quickest return to equilibrium, what we call critical damping, a critically damped harmonic motion. All right? That is a case where we have a system where we want it to return to equilibrium as much as possible. We don't want it to oscillate like it does in the underdamped system. We don't want it to slowly return to equilibrium. We balance those two out, well, the damping and the restoring. We return to equilibrium in the shortest amount of time. Now, this type of system is important for things like a car suspension, okay? Basically, the suspension is going to be like the spring. It's going to be related to K. The stiffer that suspension, okay, the more it's going to restore the equilibrium of the car, or restore the position of the car to equilibrium. Now, if your suspension is too stiff, it's not going to absorb the shocks from like when you hit a pothole, okay? It's going to be very stiff, and your ride's going to be very, very uncomfortable. If your suspension is too weak, it is going to, basically, the wheel's going to, go past equilibrium so fast, it also won't be a great ride. So a really good, well-tuned suspension is going to have just the right amount of restoring force. But you have shocks there to add the dampening so that once you go over a pothole, you hit something, that wheel returns to equilibrium as quickly as possible. Without shocks, your suspension would cause your car to oscillate up and down. So if your shocks are gone, you'll hit a bump, you'll feel the car bounce up and down a few times. Again, if the shocks are too overwhelming with their damping force, you'll hit a bump and it'll very slowly take time for the car to wheel to come back to where it's supposed to be. Now, why is this important? Well, your wheels are very, very important in keeping your car on the road and keeping control. Every time you hit a pothole, you can lose control of the car. If it's not returned to equilibrium quickly, that particular wheel may not be in contact or enough contact of the road to keep the car going where you want it. So again, here is underdamped harmonic motion. And here are examples of overdamped, critically damped, and underdamped. Again, the best example of underdamped motion would be just simple harmonic oscillator oscillating in the air. For overdamped, we can imagine putting in a beaker of molasses or really thick oil. Okay, it's going to be very hard for that mass to move. And we're going to offset it, and it'll slowly come back to equilibrium. If we put it in, low viscosity fluid like water, that might be the closest thing we have to critically damped. Again, you'd really have to match the spring well to the viscosity of the water to get that.